Okay, so for exam 4, we just have a few questions. Most of them were the big hypothesis testing ones, so we're going to go through those. So our first question here that we want to go through is, a researcher examines whether the over-the-counter cold medication has an effect on mental alertness. A sample of n equal to 16 participants is obtained. Each person is given a standard dose of medication 1 hour before being tested on a driving simulation task. For the general population, the score of the simulation tasks are normally distributed with a mean of 60 and a standard deviation of 8. The individuals in the sample had an average score of M equal to 56. Excuse me. One thing I want you to understand is, notice that we are using a population standard deviation, which means that this is going to use our z-test. Okay, z-tests are with our population. Also notice we're using an average score here. So specifically we're going to use the z-test where we do the mean minus the mean of the sample minus the mean of the population divided by the standard error. Okay, again, and that is because we are using an average of a sample, and then we're using the population standard deviation, so that steers us towards the z-scores, and then the average sample puts us towards this one where we're using the standard error in the denominator. Oops, I didn't quite mean to go forward yet, but we'll go ahead and go that way. So on the very first portion, it says, can the researcher conclude that the scores of the driving simulation task are significantly different after the medication using a two-tailed test at alpha of 0.05? So we're going to make sure that we state our null hypothesis, alternative hypothesis, critical z-value, our z-score, our decision, and our conclusion. So first off, let's start off with our null hypothesis and our alternative hypothesis. Since we're using a two-tailed test, we're going to say that our null hypothesis is that our mean is equal to the mean of the population, which is 60, which means our alternative hypothesis is going to be that our mean is not equal to 60. Remember, for our two-tailed, we just do equal or not equal for our null and our alternative hypothesis. So the second thing we need to do is we need to talk about our critical z-values. Since we're using a two-tailed test with an alpha of 0.05, our z-critical is automatically going to be plus or minus 1.96. On one of the PowerPoints where we talked about this, we listed out those critical z values in a chart. So the cool thing about the z-values is they don't really change. A two-test with an alpha of 0.05 for z is always going to be plus or minus 1.96. So then the next thing we're going to do is we're going to find our z-score. So again, remember we're using our z is equal to m minus mu over the standard error. So if you remember from the previous slide, just kind of as a note, our n was 16, our mu was 60, our standard deviation was 8, and the mean of our sample was equal to 56. So what we need to do first is we need to find that standard error. So remember, standard error is my standard deviation divided by the square root of our sample size. So this is going to be 8 divided by the square root of 16, or 8 divided by 4, which is going to give us 2. So now we can come back up here and do our z-score. So we're going to have 56 minus 60 divided by 2. So this is going to be negative 4 divided by 2, which is going to be negative 2.00. And I always like to go ahead and do my decimals when we do z-scores, because we do them out to 2 decimal places. All right, so our next thing is we're going to make a decision. And what we have to determine when you're thinking about this, so I'm going to do my little thing over here, is you have a z-score here at a negative 1.96. We have a z-score here at a positive 1.96. If our z-score that we found in step 3 here, where we found our z-score, lies in this area, which is lower than negative 1.96, or it's higher than 1.96, we are going to reject the null. So this is to reject, and this is to reject, either one of those. But here in the middle, this is where we do not reject, if it falls in between them. Sometimes it's easier to think about this if you draw a quick standard curve and kind of highlight what your area is. You'll notice that our z-score is negative 2. So our z-score maybe falls about right here, negative 2.00, which is in our gray shaded area where we are going to reject. So for our fourth step in this, when we make our decision, we are going to decide to reject the null hypothesis. Now, there's a next step that says write the conclusion. So when we write this conclusion, what I want to know is, what does it mean to say that you're going to reject the null hypothesis? And what this means is that there is significant, I'm not going to write the whole thing out, I'm just going to tell you what it is, that there is significant evidence to show that this over-the-counter medication has an effect on mental alertness at least a 0.05 alpha level. Okay, so when you do your conclusion, it's where you're really specifically telling me what it means, that there is an effect of whatever the treatment is on whatever the measurement is. Okay, so there's this medication has an effect on the mental alertness for this driving simulation task. So that's what we're talking about when we talk about the conclusion. So the decision is whether you reject or you don't reject, and then the conclusion is how you tell me what that means. So let's do the second part to this. Oops, there's my alpha levels. Sorry, I didn't realize it came up like that. So let's do the second one. Look, there's our alpha levels again. So we have the researcher conclude that the scores on the driving simulation significantly, but this time we want to do a one-tailed at an alpha level of 0.01. And we're also saying that it is lower. So we want the value, we're saying that the medicine is affecting their scores on that simulation task by lowering them. So whenever we do a one-tailed test, whenever I do my hypothesis, I always start with my alternative, and that's when I say, I want it to be lower. So I want to say that my mean is lower than 60. So my alternative would be the opposite of this, which would be my mean is greater than or equal to 60. So whenever I'm doing a one-tailed, I always start with my alternative hypothesis and then write the opposite being my null hypothesis. So now for our Z critical. Okay, so I got the chart up here this time. We are doing a one-tailed, so we're going to use this column right here. And our alpha level is 0.01, which is going to be this guy right here. So our critical value here is going to be 2.33. And I'm going to just draw out real quick up here at the top my very poorly drawn bell curve here. And what this means is I have, and by the way, this is going to be a negative because I'm looking for it to be lower. So I want a negative 2.33. And anything that falls to the left of that, this would be to reject. And anything that falls to the right of this is not reject. Okay, so let's find our Z-score. Actually, we don't really even need to find our Z-score. It's actually going to be the exact same Z-score as we had for our previous step for 1A. So our Z-score is not going to change. Our Z is still going to be negative 2.0. And the reason it doesn't change is because I haven't changed any of my values. My sample is still 16. My mean is still 60. My standard deviation is still 8. my mean of my sample is still 56. So nothing of those values have changed. So changing the type of one-tailed test versus a two-tailed test and changing your alpha level, that's not going to change your z-score in these, because all your values are going to stay the same as far as plugging them into that z-score formula. It just changes your critical value, and it changes your null hypothesis. So now we're going to make a decision. So -2 falls here, somewhere to the right of -2.3, which is in my do not reject. So on this one, we are going to say we do not reject the null hypothesis. Remember that when you're doing these, we never say that we accept the alternative. We only ever either reject the null or do not reject the null. So when we're talking about not rejecting the null, that this means that there is not enough evidence to show that the medication lowers, remember, because we're doing a one-tailed, so we're talking about lowering, does not show that the medication lowers the mental awareness at a 0.01 level. Now, had I done the same level as I had the first one and not changed that alpha level, notice my critical would have been 1.645, and then it would have been significant. And those are where we get back into those type 1 and type 2 errors. With such a high alpha level on this, I am really starting to get close to having that type 1 error when I don't reject when I should have rejected. So you got to be really careful with your alpha levels on these guys. All right, and then the last question is we want to do our Cohen's d, or effect size. So remember, when you're doing this guy, you're going to do the mean of the treatment minus the mean of the not treatment, divided by the standard deviation. So in this case, what we're doing is 56 minus 60 divided by 8. So this is going to give us -4/8, which would be a -0.5. But when we're doing these measures, or these size effect, we don't really ignore, we kind of ignore the negative and just say that our size effect is 0.5, and that is going to be a medium effect on the data. Okay, so let's look at our second question. Here it says the expected value that a treatment will reduce a score on a variable. If the alpha level is at 0.05, what would be the critical t-value for a one-tailed test with an n equal to 15? So remember, when you're doing a t-test, we don't use the n for for determining our critical value. We actually use the degrees of freedom, which is the n minus 1. So this would be 15 minus 1, or 14. So when we do this, we're going to be looking at this row right here. And then we want a one-tailed test. So we're going to look at the first row here for our percentages. Our alpha level at 0.05, which would be this guy. And this would be our t-score. Now, since we are doing a one-tail, it's either going to be negative or positive. So if we go back to our question, it's asking, it says reduces the score. So reduce would be a negative value. So that means that our t-score wouldn't be a positive 1.761, but it would be a negative 1.761. So when we're doing those one-tailed tests, we really need to pay attention to the wording. And if I just said it would increase the score, then that would be a positive. But since we said it was going to reduce the score, that would be a negative. So just kind of make sure you're reading those problems to make sure you realize whether it's going to be a positive or negative. And remember, for two-tailed, it's either positive or negative. I don't care which one, plus or minus. But when we do the one-tailed, we have to say whether it's going to be positive or negative. Just look at the wordings to see if that's a negative value or a positive value. All right, so question number 3 here. Says a sample is selected from a population with a mean of 50. After a treatment is administered to the individuals in the sample, the mean is found to be the mean of the sample is found to be 55 and the variance is 64. So one of the things I need you to understand here is notice that actually there's two things. One, I'm giving you variance, not standard deviation. Okay, so it really should be S squared. I'm sorry, it doesn't say that, but I'm giving you variance instead of standard deviation. So first of all, we need to find the standard deviation. Remember, standard deviation is S is equal to the square root of S squared. So in this case, this would be the square root of 64, which is going to be S, or 8, excuse me. So our standard deviation for our sample is 8. The second thing is we are given the standard deviation of the sample. So when you have the sample standard deviation or variance, that is immediately a t-test. Now, as far as how you do a t-test, as far as computing the actual score, it's pretty much the same thing, except instead of using the population standard deviation, you're using the sample standard deviation. So t is equal to the mean of the sample minus the mean of the population divided by the estimated sample error, or sample error, standard error, excuse me. Oops, sorry, I didn't mean to go with that. And so the estimated standard error is the S divided by the square root of n. So your standard, your sample standard deviation divided by the square root of n. Sorry, I keep messing up on that. All right, so kind of remember that when you're given the sample's standard deviation, you have to use the t-test. All right, so let's look at our first question here. Again, just kind of as a remember here, our mean for the population was 50. Our mean for the sample was 55. And our standard deviation for the sample was 8. And we are going to use a t-test on this one. So we're going to start off with an n equal to 4. So in this first example, our n is going to be equal to 4. And we want to calculate, we're going to go through the entire thing of our hypothesis testing, and then we're also going to calculate our Cohen's. So starting off with our hypothesis, we are doing a two-tailed test, so that means our null hypothesis is going to be that our mu is going to equal 50, and our alternative hypothesis is going to be that our mu does not equal 50. All right, so the next thing we're going to find is we're going to find our t critical. Since it is a two-tailed test, this is going to be plus or minus. We're using our n equal to 4, which means our degrees of freedom is 3. So that means we're going to be looking at this row right here. Since we're doing a two-tailed test, we want to use the second set of percentages, and we're going to do an alpha of 0.05, which is right here. So our critical t value is going to be plus or minus 3.182. So now we are going to find our z-score. So in order to do that, remember, it's not our z-score, excuse me, our t-score. So t equals m minus mu divided by the estimated standard error. And remember, estimated standard error is my standard deviation divided by the square root of my sample. So this is going to be 8 divided by the square root of 4. So this is going to be 8 over 2, or 4. So now I can come back up here. I'm going to do 55 minus 50 divided by 4. And we do that math, we're going to get 1.25. And again, you're still thinking the same way we were doing on our z-score. If this is my critical value, 3.182 negative, and positive 3.182, I'm going to reject if it's here or here. But if it falls between them, I'm not. Well, 1.25 is maybe about right here, 1.25. Think that this is your 0. Well, that's definitely in my do not reject. So my decision here is that we do not reject the null hypothesis. I'm going to be a little bit lazy because I'm running out of room. So that means that at an alpha level of 0.05, there is not significant evidence to show that there is a critical difference between the population and the sample for this particular treatment. Okay. Now to do our Cohen's, it's the same way. We're going to do our mean difference, so 55 minus 50, and then we're going to divide by our standard deviation, which is 8. So this is going to be 5 divided by 8, or 0.625, which is, again, a medium effect. Okay? Now, for the second part of this question, we're going to do the exact same thing, but this time we're going to use an N of 16. Everything else is going to stay the same. We still have the same population mean at 50. We still have the same sample mean at 55. Our standard deviation is still 8. But now we have N equal to 16, which means our degrees of freedom is 15. So our null and alternative hypotheses are going to stay the same because we're still doing a two-tailed test. So we have the mu is equal to 50 for our null, and our alternative would be the mu is not equal to 50. So then for step 2, if we look at our degrees of freedom at 15 and our two-tailed at alpha 0.5, we get that this is our critical. So our T critical does change. And the reason that it changes is because our degrees of freedom has changed. So this will be plus or minus 2.131. And our Z-score is actually going to change as well. So again, Z equals my sample mean minus my population mean over my estimated standard error. And we're going to remember my estimated standard error is my deviation over the square root of my N. So this is going to be 8 divided by the square root of 16, or 8 divided by 4, which is 2. So up here we're going to have 55 minus 50 divided by 2. So 5 divided by 2, which is going to get us a 2.5. And again, if you think about it, oops, I'm sorry, I didn't mean to do that. This right here is my 2.131. 2.5 sits right here, 2.5, which is in our reject area. So for this one, for step 4, we are going to reject the null hypothesis. Okay, so changing that in changed whether or not we were rejecting or not rejecting our null hypothesis. Okay, it's a really important thing for you to understand when we're doing these t-tests, that changing that in value, changing the number of people in your sample is going to affect whether or not your experiment shows a significant difference. That's why we get those type 1 and type 2 errors, especially when we have small sample sizes. We want to try to have larger sample sizes because larger sample sizes guarantee us avoiding these types of errors. So in this particular one, when we make my decision or make my conclusion, I'm going to say, yes, there is a significant difference between my population and my sample at a 0.05 alpha level. And then let's look at our Cohen value again. And it's going to be our 55 minus 50 divided by 8. So that's still going to be 5 over 8, which is going to be 0.625. Notice that our Cohen, our effect level didn't change. And mainly it doesn't change because the effect level is not affected by my sample size. They don't use that as part of my thing. It's only affected by the mean of my population, the mean of my sample, and my standard deviation, which don't change based on my population sample size in this case. So that's kind of the last question. If increasing the sample size actually increased the likelihood that we would reject, but it did not affect the measure of the effect size of our information there. So again, remember, increasing our sample size does affect the likelihood that we would reject our null hypothesis.